actually even think of things like inheritance as a mechanism for live updates. Here in this example, derived inherits from base, and after derived is created, I add a new method to base, and it's instantly available on derived. Now, it's actually kind of unlikely that we'll actually do something like this at runtime. Instead, what is a little bit more likely is we might do something like this across versions of this underlying code. So let's extend this idea across versions. Let's say that base starts with a method f, and then later in a different version statically has a method g added to it, and then at runtime has yet another method h added. And let's compare inheritance, composition, and alternate approaches like object construction. In the inheritance case, we can think that we're always getting a live view of the underlying data in that original base class. So the derived will have both f, g, and h all available, and we don't have to do anything explicitly. In the composition example, the composed example will have f, and it won't have g or h because we have to go and manually implement those. We have to manually, basically effectively copy these over to make these available. And now they'll have h, but unless we implement them, it won't have them. In the object construction approach, here we can actually say, okay, take f and also take g that's later, but don't take h. And we can even pick and choose which of these types of updates we want to include and which of these types of updates we don't want to include. In fact, we can even manually make this not too different than the composition example by manually picking out which of the methods we want from the base class. And you can see we have a number of different choices for figuring out how changes might cascade. This might lead us to a richer understanding of the difference between composition and inheritance, in that if this base class is something like a NetworkX digraph with a bunch of methods and a bunch of changes that occur between versions, do I really want to be chasing the changelog of NetworkX every time they add a method? Do I want to implement that through my composition example? Probably not. Probably if I'm going to subclass a NetworkX digraph, I want to do one tiny thing and then make it transparent to everything else. And so in the case where I want to accept changes as they come and just do one tiny piece of work and I don't want to track this forever, I actually may want inheritance. Whereas if this is something that I'm paying very close attention to and I want to be very careful about only bringing in changes as I become aware of them, then composition may be a better choice. It gives me a little bit more control, but with some corresponding additional responsibility. Consider that we can even implement some wild object construction type approaches using things like collections.chainmap, and we can find some other ways to represent the idea of snapshots or live views via some kind of scoping mechanism. Here we have a dictionary, and in this snapshot dictionary, we've made a copy of the entries, a shallow copy of the entries in the base dictionary, which means if we make a change to the base, it is not visible on the snapshot. If we make a change to the snapshot, it is not visible back onto the base. However, if we make this a chain map, then if we make a change to the outer layer, the live view, it'll be visible on the live view, but it won't cascade down to the base. But if we make a change to the base, it will be visible on both layers. And since there's no way for us to make this a live view without that layering, there's no chain map that just doesn't distinguish between the different layers. There really isn't a way that we can have the live view then go affect the base layer. It's always going to shadow. And in fact, the shadowing problem is something that may lead to bugs or errors in our code. It's something that we should be very careful to be aware of. In other words, remember, when we're performing operations on things like lists in Python to clear them out, there is a material difference between saying x's equals empty list versus x's dot clear or del x's with a slice for the whole thing. In this case, if there was another reference to x's, another name referring to the same data, only x's will have been rebound, but y still contains the original data. We didn't go and clear out the original data, so y is going to represent something that might or might not be stale. Whereas in the case of the dot clear or the del with the slice, we will have updated this, we'll have mutated x's in place, and the change will be visible on x's and y's. Which of these two we want is going to be dependent on our circumstances, but it's important that we understand that there is a very subtle difference here. Is there a subtle difference between number 2 and number 3? Maybe. I guess if this is a set, then we can dot clear a set. But this syntax doesn't make sense on a set because we can't do slices of a set. So probably, in most cases, what we want is number 1, if we want to only change x's but not change y's, or number 2 if we want to change both of them, or if we want that change to be visible on both of them. This is why when we look at things like sys.path, well, there's a lot of different ways we can manipulate sys.path to add an extra location to the sys path at the beginning or at the end. And some of them will work and some of them won't work. Well, the reason that some of these don't work is a consequence of shadowing. Here we have 4 different approaches, either appending or inserting. If we make a mutating change to sys.path directly, that changes the actual sys.path. Well, we've updated our path. Similarly, if we do this with sys.path.append, exactly the same thing. If we say from sys import path and we say path plus, what this is going to do is it's going to make a copy of sys.path and create a variable in this module scope called path that has shadowed the original sys.path. So these two won't work. However, if we do sys.path equals sys.path whatever, we're going to assign it back into the sys module, and both of these will work. Shadowing is how we refer to what happens when we have some kind of multi-layered structure. And just like in that chain map or in the sys.path example, we create an entry at one layer that is maybe blocking view to the other layer, shadowing it. The shadow is blocking out the light, as you might think. Here, if we have a base type and it has some attribute, and we have a derived type with some attribute here, if we manipulate this attribute on the base type, we can see it gets changed when we look at it through base.x or through derived.x. Because when we do derived.x, it's going to trawl the MRO of derived, and it'll look in each of those places to try and find that .x. Well, it'll find it on base. It'll find the thing that we manipulated. If we make the manipulation on derived, a mutating manipulation, it'll be visible in both places because derived.x is going to trawl the MRO, find the .x that existed here, and it's going to change it in place. However, if we do an assignment of base.x, note it'll be visible on base.x and derived.x. But if we do an assignment on derived.x, what'll happen is it'll only be visible on derived. If we look at what's happening here, with this assignment, what we're doing is we're adding another entry into the dictionary representing the local data, the attributes for the derived class, and that value is shadowing the value of x in the base type. Note that if this underlying value is immutable, this is something which we have to be quite careful about, because if it's an immutable value, we can't do a plus plus or a minus minus. We can't change it in place. And so there is a material difference between saying base.x and derived.x. Derived.x will only be visible on derived, but it won't write back to the base. Base.x will be visible on base and derived. And there's a sequencing here where if we do these in the wrong order, we can see that this has now blocked these updates. This means that if we happen to have some immutable data that is shared in some inheritance hierarchy, we need to be very careful to update it in the place that we want it to be updated. That is to say, we need to update it at the level such that everything at that level and below reflects that change. And we also have to be careful that we don't have some shadowed writes that are blocking any changes that might be visible otherwise. And so if we were to first do this assignment and then do this assignment, what we might need to do is we might need to remove this entry so that passes through. Otherwise, we won't see that pass through, and that original shadowed write will block us. So why does this matter? Well, this is again a source of common bugs that we may see in our code. It is very much the case that shadowed writes, problems with sys.path, problems with our inheritance hierarchy are all things that we might see in our code that lead us to question, what's actually going on here? Wait, I made a change here, but I see it over here, or I made a change here, but I don't see it over here. We either get no action at a distance that we want, or some spooky action at a distance that we don't want. Understanding the difference between live view and snapshot view is not about debugging what the problem is in your code, but about putting a set of terminology behind. Well, sometimes we want one, and sometimes we want the other.
Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.